We are the Aerodesign SAE USB team. Welcome to the technical presentation for our 2020 project, the Turpel 14. These are the topics we will be talking about. The process followed by the team is shown in this Fishbone diagram. The main tasks are listed for each design stage. The preparation for the competition started with an evaluation of the 2019 design. It was the heaviest of the regular category. The nose landing gear failed during the flight rounds. The team organization had to be improved. To correct this, theses were developed on structural elements. Cabin, a lean method to manage projects, was applied. Computational fluid dynamic analysis, airfoil design, and control studies were added. The mission is to design a radio-controlled aircraft that takes off in 50 meters with a payload greater than 5 kilograms, makes a 360-degree turn, and lands without structural damage. The aircraft length plus wingspan must be less or equal to 3.2 meters, and needs to comply with requirements regarding the propulsion system and electrical components. A score analysis concluded that the main goals for the design are to have a higher payload to increase the flight score, have an empty weight equal to the reported one to increase the accuracy score, and improve the report score. Moving on to the conceptual design. The maximum takeoff weight was estimated. Databases for monoplanes and biplanes were used as these are the most common designs for the geometric restriction. Initial dimensions were computed and the obtained values were compared to the databases and found to be appropriate for the requirements. To select the propulsion system, results from a 2019 Turkey power test were used. Electric engines were ruled out due to economic and logistic reasons, since the access to laboratories and equipment was denied. The OS with the 12x6 propeller was selected due to its higher power for the estimated speed range. With this, geometries were iterated with a MATLAB code that integrated aerodynamics, stability, performance, and structural studies through 5 phases. Geometry generation based on the restriction, calculation of the aerodynamic coefficients, verification of static stability, calculation of maximum takeoff weight and landing distance by differential analysis, and estimation of empty weight. A sensitivity analysis was made to evaluate the influence of parameters on the flight score. B1 and M1 are the biplane and monoplane obtained from the code. Thrust, wing surface, and maximum lift coefficient are the most important factors for the score. This was considered for airfoil optimization. B1 is the best choice since it complies with the geometric restrictions and has the highest surface, payload, and flight score. For the preliminary design, several features were added to improve the critical aerodynamic values of the aircraft. An extensive study of the most common high-lift airfoils was done. The Selif 1223 and the FX74 airfoils were chosen. Both of them have high lifting capabilities and the second one has great aerodynamic efficiency. These were interpolated, resulting in 18 new airfoils, of which only 2 were used on the final design. The combination shown on the screen gives satisfactory results. Regarding the horizontal stabilizer, an Epler 387 reverse airfoil was used to correct ground roll issues observed in last year's design. Wing platform was achieved iterating geometries until one that meets competition requirements with the best performance was found. A biplane with no stagger and a tapered forward sweep was selected. End plates were included to reduce wingtip vortices, increase lift capabilities and aerodynamic efficiency, and improve stability. A plate fuselage was used to generate less drag due to skin friction, reducing its wetted area and matching the upper surface with the lower wing surface to achieve an overall streamlined shape in the wing. The final configuration was evaluated. Most of the results show a good correlation. Computational fluid dynamics was used to study lift variation with the angle of attack until the stall is reached. The study allows seeing wind flow behavior at those conditions, where flow separation is noticeable. All these new features and more accurate results were responsible for the greater performance achieved compared to last year's design, allowing us not only to optimize the critical aerodynamic factors, but also to have a more precise approximation of how our aircraft will behave. Data on the flight conditions in São José dos Campos showed that the average altitude is above 1,100 meters, and 95% of the time is greater than 900 meters. Therefore, altitudes between 900 and 1,400 meters were selected for the studies, using the International Standard Atmosphere Model. The maximum takeoff masses were computed for the altitude range by numerical integration of the equations of motion considering the ground effect. The performance speeds were calculated. With this, the stability of the design was studied. The aircraft is statically stable since these conditions are met. The height of the center of gravity varies with the payload and is located between 30 and 35% of the mean aerodynamic core. The center of gravity changes as the fuel is consumed. The neutral point and the static margin were computed to guarantee longitudinal stability without affecting the performance of the aircraft. The elevator was dimensioned using last year's dimension as initial parameters due to the satisfactory results obtained. The deflection for trim was calculated for the range of speeds established and has a maximum deflection of 20 degrees to improve rotation during takeoff. The rudder was dimensioned following the same methodology. A minimum deflection was established to guarantee lateral trim and a maximum deflection of 20 degrees was selected. The ailerons were placed between 66 and 90% of the lower wingspan, considering a stall of the upper wing and manufacturing processes. A helix angle higher than 0.07 was obtained and a satisfactory bank angle response to the aileron deflection was found. Regarding the handling qualities of the aircraft is located at Class 1 within phases B and C. For dynamic stability, for the longitudinal mode, it was found that the aircraft is level 2 for fugue mode, and for short period it reaches level 3. When assessing the lateral directional mode, it was necessary to improve lateral stability. Two options were considered: end plates or a diagonal angle of 4 degrees, to reach a value close or equal to 4 seconds in the spiral mode, to reach at least level 3, using as reference previous prototypes. As stated in the aerodynamics study, the geometry with end plates was selected because it makes a larger improvement in roll stability, is easier to manufacture than the diagonal angle, and improves the aerodynamic efficiency. The time domain response of the aircraft shows that the longitudinal response converges, and the lateral directional response diverges. Despite this, using theoretical results computed by the team, the experience in previous competitions, and the design decisions made for the present year model, is prominent that the aircraft is reliable and maneuverable. To verify that the aircraft is capable of flying the selected range of heights, a performance study was made to calculate the rate of climb, descent, and ceilings. For landing, ground effect was considered. The landing distance is considerably less than 100 meters, so brakes were not incorporated. The mission profile was made to guarantee that the mission can be completed. The estimated distance to travel is 600 meters, considerably less than the aircraft range, and its endurance is greater than the maximum estimated time of the mission. To determine the critical flight conditions, an altitude of 900 meters was used to elaborate a VN diagram. A load factor of 3.47 with a speed of 19 meters per second was obtained. The ground loads were computed for the maximum takeoff weight following the Federal Aviation Regulations Part 23 for 4 landing conditions. The highest load is reached when landing in one main wheel. By modeling the plane as a rigid body, the lift force and moments distribution across the lifting surfaces were computed using ABL at critical flight conditions with maximum deflection in the control surfaces. The shear force, bending, and torsion moment diagrams were constructed, and the critical sections were identified. Several discontinuities can be observed on the wing diagrams associated to the joint between wings. No discontinuity was considered for the bending and torsion diagrams of the lower wing due to the small magnitude of the loads transmitted by the joint. The wing experienced higher loads in comparison to the stabilizers, which follows the initial suppositions. Finally, the hinges moments were obtained by the equation proposed by Nelson. Moving on to the detailed design. The materials were selected with decision matrices that were used to consider cost, weight, and mechanical properties. These materials were considered and a safety factor of 1.5 was selected. For the wing beam design, Tresca and SAE failure criteria were used. The beam consists of 2 different cross-sections distributed as shown. This reduced costs and facilitated disassembly for the transfer of the aircraft to Brazil. The union between the wings consists of a C-shaped column. The horizontal stabilizer has two circular beams made of pole-throughed carbon fiber, and the vertical stabilizer has one made of the same material. The fuselage must be removable to facilitate transport. Therefore, it consists of a flat central plate fixed to the lower wing and a non-structural removable outer cover attached to the lower wing. The main landing gear consists of two carbon fiber reinforced wing ribs. To ease travel logistics, the ribs are mounted on carbon fiber tubes that fit in the inner part of the wing beam. The previous nose gear failed during the competition, so 3 new models were designed and the most reliable one was selected. 4 different wheel designs were proposed. These were studied in 7 different angular positions with an equivalent load of 300 newtons for the landing impact. The selected design was optimized and its total mass was reduced by 29%. The distribution of the electrical components was established. The HS65HB is the lightest servo motor available, showed the lowest percent error in previous tests, meet the required torque for all the components as well as the maximum deflection requirements. Having one model for the system increases reliability, thus it was selected for the components of the system. A battery discharge test from 2019 showed that the battery lasts 37 minutes at maximum power consumption. AWG22 wires were selected using as criteria the maximum current of the system. Bolted joints were calculated for assembling the final model. Epoxy resins were selected for the ribs and beam joints. The mass of each component of the aircraft was estimated. The propulsion system, materials for the construction of the structure, and the electrical system components were measured. A pseudo-static model was considered in order to obtain the divergence and control reversal speed. The divergence speeds will occur after 200 meters per second. The real divergence will be outside flight regime. The control reversal speed will not be reached in the flight regime, but the phenomena will occur before divergence. A simple model to study flutter was followed. Flutter will occur at 37 meters per second in the horizontal stabilizer and after 100 meters per second in the wing, outside the flight regime. A later study, considering a 95% reduction of the wing stiffness, showed that under this condition flutter phenomenon will not occur during the mission. Real flutter speeds will occur at lower speeds, but considering the low speeds reached by the aircraft and the higher stiffness of the structure, no flutter will occur during the mission. Conclusions. The aircraft could not be built and tested due to restrictions to access to the university and model airplane runways. However, most of the design objectives were achieved. The project was successfully carried out remotely. Thank you for your attention.